All right, welcome everyone to Western AI Data Quest presents Excel versus Python regression. We're going to be going over the differences in Excel and Python in regression and sort of what regression is and how you can use it to your advantage. So first of all, what is regression? Regression is a machine learning tool that is widely used and it shows relationships between variables. It yields a continuous result rather than a discrete result. So instead of like categorizing different pieces of data, you're getting this sort of single value prediction. And these model predictions that you get are sort of based on mathematical functions. So what you see on the screen here is a linear function and data points around it. So what this is it's the regression line and it's trying to match that data to its best possible and least error that it can. And then all the predictions that you will make will be based on points on that line. So the closer the line fits the data, the better your actual result becomes. So as the numbers of different data features and variables that you have grow, the regression can actually increase in complexity and you can actually include all of these different independent variables within your actual mathematical model. So the most simple form of regression is linear regression. So linear regression, like I mentioned earlier, is just a mathematical function where that mathematical function is a linear function. So if you look at an equation all of you are probably semi-familiar with from like grade 9 math, we know it as y equals mx plus b, but you can also look at it as a function of x equals a weight times a variable plus some sort of bias. So on the image, you can see there's different data points, and not all of the data points are the same distance from that line. And that's basically just showing that there's different amounts of error depending on what data point you're looking at. And the goal with regression and basically any machine learning sort of algorithm is to reduce that error so you can get as accurate of a result to what you want as possible. So that's done by editing these values. So the weights, which you can think of as the slope in this case, and then the bias, which you can just think of that intercept. So as we sort of look at more data, we can adjust these values to better fit the data we have at hand and to better produce predictions for data that we might be missing. So how you sort of actually get to improve your model is through loss functions and optimization. So you try to minimize what's considered a loss function. So a loss function is a mathematical expression for the current state of that machine learning model, and it'll provide a numerical look on how well a certain set of weights perform. So we talked about having the weight and the bias, so we need to be able to compare every different variation of them in a sense that provides insight into whether or not we're actually improving. And the goal is to find that minimum loss and reach that sort of bottom of the bowl. So you have the most optimized solution, or at least something close enough that you're comfortable with. So now we're going to look at just a couple types of loss functions. So listed here, we have mean squared error, mean absolute error, mean biased error. There are a few more you can see, but you can see the equations for at least mean squared error and mean absolute error. So if you guys are a little uncomfortable with this, I'll break it down. In the mean squared error, which is the MSE you see there, basically all it's saying is it's the sum of all the errors squared. So where the line is, that's your prediction, and then where the actual data point is, that's your actual value. So if you subtract those values and square it, you get your squared error, and then when you divide it by the sum of that by all the data points, you now have your mean of your squared error. So your mean absolute error is very similar, but instead of squaring them, you're just taking the absolute value of that difference, adding them up, and then dividing them by the total number of data points you're looking at. And this will give you the mean of your absolute error. So there's different reasons why you use these different sort of metrics. For example, mean absolute error kind of helps with outliers. If you have certain points in your data which you feel are not as descriptive to the whole data set, a mean absolute error will give less meaning to that large difference between your actual regression line and your data point. So you guys can sort of look at different types of errors and see which metrics you feel best fit the machine learning models you decide to make. And then there's the concept of multivariate linear regression. So when we looked at that previous plot, we looked at what's called univariate, which you're dealing with a single x vector of data. So if you look at any standard two-dimensional Cartesian graph, you have a y-axis and you have an x-axis. And in that case, basically what you're comparing is one independent variable on that x-axis and trying to predict how that one independent variable affects that dependent variable on your y-axis. With multivariate, you have more than one independent variable. So this is in the case of if you have a data set with multiple features, different components that you're looking at to actually predict that single value. You can look at multivariate linear regression. So on the graph here, we actually have weight and horsepower to define miles per gallon. So you have two variables that are independent, and they're defining a single dependent variable. But this can get more complex than just 2 or 3 variables. You can get 4, 5, 6, 17, 18. At that point, you can't exactly plot it as easily, but you still get that same usage out of those independent variables. So the first thing we're going to look at today when we pass over to Emiliano is how you guys can use Excel for regression. So I'm sure some of you guys may not have much of a background in coding, and you've probably used Excel a fair bit. So Excel is a great tool for initial analytics and can provide regression options for you guys. But the main benefits is that it's fast, it's great for that initial analytic phase, and it's good for basic ordinary least squares. Some of the cons that come with it is there's a lack of support for more complex machine learning models. Regression is fairly simple in what you can do in Excel. And if you want to, pursue something like a more complex machine learning model, you might want to look into other options like Python. You might have difficulty working with larger data sets just because it doesn't have the same functionality that other resources do. And there's limited visualization in comparison to things like Python. This might be kind of surprising to some people because, we've all made graphs in Excel. It's not exactly rocket science, but with understanding of, different tools like Python, you actually get more of an ability to actually look at your data and visualize it differently. And then once we cover Excel, we're going to go over Python for regression. Some of the benefits is that it has a great open source libraries. So things like TensorFlow, scikit-learn, Matplotlib, all these different tools that if you guys aren't familiar, hopefully you will be familiar with soon. And then you can use more analytical interfaces like Jupyter Notebooks or Spider, where you can, notebooks tend to allow you to visualize more sort of components of your data and actually provide more of a interface for it. If you guys are familiar with Anaconda, you can use conda generation to make your sort of production of your actual models a little more like less complex and a little easier just to actually get it out. And then you have the support for more complex models. So right now we are going over regression, but if you've ever wanted to play around with things like k-nearest neighbors or even neural networks, Python has support for all of those, and it's widely used to actually create those. Some of the cons when it comes to using Python is there is a steeper learning curve, and setting up it will be slightly more difficult than your Excel. Excel is a lot more nicer in that sense. So now I'm going to pass it over to Emiliano, and he's going to run you guys through some of the stuff you can do in Excel with regression.
Yeah, sure. Hey guys. So yeah, we'll be going through the regression portion of the workshop now. So the first thing I'm going to do is I'm going to drop a link to the Google Drive for the dataset that we'll be using. We'll be using this dataset for both Excel and Python. And now I am going to follow it up by sharing my screen. Sorry, I just have to open Excel first. Okay, I don't think Excel's showing up, so I'm just gonna share my screen. Should be fine. So the first thing I'm gonna go and do is just like just so if you guys want to follow along, I'm gonna go into the chat. I'm gonna open the link that I sent, and then I'm gonna download the CSV dataset and drop it into Excel. So just showing you guys doing that. So just gonna download it. Already have it. And then the next thing I'm just gonna do is I'm just gonna go on my Mac and then click on it.
1 second, Emiliano. I don't know if we got the link in the chat.
Do you not have the? Oh, sorry. I think I had it to private messages, but there we go. So everybody should be able to see that. So that should be the link. And the next thing I'm going to do is, since this was like initially set up in a comma separate value, I'm just going to transform it to a macro enabled workbook. Doesn't really need to be macro enabled, but it's just nice. And we're just going to quickly go over some of the basic steps to actually perform.
Emiliano, looks like the data set the link you sent is not a public viewing link. If you can change that.
Oh, is it not? Okay, sorry about that. Let me make sure that it is. Okay, so everybody, the second link should be fine. So anybody with the link should be able to open that data set now. Okay, so now that we have our, the data set that we're gonna be working with is just like a basic housing data set composed of like predicting the price based on a couple features. So here we see our response variable, response Y variable, whatever you want to call it. They're just synonyms for the same thing, is the price variable. And then we're going to be trying to predict the price of the house based on that, all these features. So bedrooms, bathrooms, square foot, floors, waterfront, et cetera, right? So Excel is great, especially if you want to just do basic, quick regression. It can even handle like multi-linear regression, which is what we're going to be doing today. Something important to notice is just like, unfortunately, Excel is, like we said in the beginning, it is limited and it only allows you to do regression on 16 variables. So the first thing we're going to go do here is just like, for the sake of simplicity, ideally you guys will be running experiments, figure out what features are the best, or for the sake of time right now, we're just going to go ahead and count up to 16. We're going to highlight these, and these are going to be the features that we're going to be using for the following analysis. So the next thing you want to do a regression is, it's actually very simple. All you go is go to data in the Excel tab, analysis tools. Oh, sorry, it's not analysis tools. It's data analysis. And then as you see here, you have like a lot of like cool little essentially click and play, and then it just does it all for you. So it's like t-test sampling, all that stuff. But for today, we're interested in regression. So we're going to go ahead and click that. So as you can see, the input wide range. So this is the prediction. It's already defaulting to price. And then all of our features that we selected are following right after. So we're going to go ahead and click OK. As you can see, we have now created a regression with 16 variables. You can't get the labels in here, but for right now, we're just going to go ahead and call them variable 1, variable 2, variable 16, right? So now the next thing that you might be wondering is just like, what do these mean? And what does this do for me, right? So if any of you guys are familiar with p-values, of course, you know, you can interpret these p-values exactly the same way as you would interpret it for like a t-test or any sort of ANOVA, which is just like you set a threshold for your p-value, and if it's less than that threshold, then you would consider it significant. So for example, here, the p-value for the intercept is below, it's 0.001, which is by most standards considered below threshold. So we consider this significant, and you would go ahead and do that for all of these. For some of them, like you see here, we might have insufficient data, or we might run into some issues with data having like no values and the like. So we will actually have like some errors, but for now, that will be up to you guys to like be able to figure out on the spot and explore your data a little bit further within Excel too. So now the next thing you're probably wondering is just like, I have all these variables, I have all these coefficients. How do I actually run a prediction on these things in Excel? So what we're going to be doing is we're going to make here a quick prediction column. I'll just color code this for now. And what we're going to be doing now is we're going to be transposing this, because we're going to be using the dot product. So we're going to do equals transpose. And then we're going to transpose this entire thing. So for those that are unfamiliar with Excel, when you actually want to perform an operation on an array like this, you have to press Command Enter on a Mac, or Control, I think it's Control Enter on Windows, or it might be Control Shift Enter, one of those two. But the reason we did this is because this allows us to now find the actual dot product between this matrix and this matrix. So for the you guys that are not familiar with the dot product, it's simply just taking the first variable, timesing it by the first variable, and then doing the same thing for this, for the second variable, and then just summing their product together. So in Excel, they have a little bit more of an intuitive way to call this operation, which is just the sum product. So as you can see, I'm just moving the little prediction just because it's going to be blocked by that. So we're going to go ahead and do this now. So then prediction, and then we're going to do this equals to the sum product. We're going to go ahead and highlight this array. Then we're going to do a comma over here. And we're going to take this in now. And then this should equal. So as you can see here, if we one of the basic things that you guys need to remember is just like here, you're going to see we have a negative value. And you go look at the price for this value and it's positive, it's 2000, it seems very off. But one thing you have to remember is that we do have an intercept, or as Daniel called it, a bias, again, just interchangeable terms here. So we have to remember to add back the intercept just to be able to accurately predict. As you can see now, our prediction looks a lot closer. It's actually very, very close to the expected value. And we can go ahead and actually just like if we really want, we can go ahead and like plot these down. One thing to remember is to lock the values of your coefficients, because if you don't lock these values of the coefficients, and then you do a little drag and drop, not this one, sorry, a drag and drop, then it's going to get all messed up. So you got to remember to lock the values of your coefficients and intercepts. As you can see, we can go ahead and now run predictions like this. Now, if you want to do evaluation of the model or the like, there's some basic evaluation metrics here, such as R squared, adjusted R squared, multiple R, which you can just take a quick look at and kind of like decipher and get an initial evaluation of your model. But you can also run like mean squared error and the like by just quickly, for example, if we want to do a mean squared error, all we would need to do is just like grab this value, which is, this is our prediction. Sorry, I messed this up. So we grab this value, which is our prediction, minus it by our true value, and this will give us our residual. So to find the mean squared error, all you really need to do is, the squared, yeah, the mean squared error. All you really need to do is just square that, and then all you're going to need to do that is like follow through with it, and then sum all of these values, right? And that will give you your mean squared error for your essentially for your little regression that you just output it. And if you're unfamiliar with the mean squared error and stuff like that, that's okay. In the following, especially in the Python notebook, I'll be going through it a little bit more slowly. But this is just to get you guys a general idea of like the stuff that you can do in Excel. You can do a lot of really powerful stuff really quickly. As you can see, we've only been going this for around 15 minutes, and we've already got a working regression with all of our predictions. But for now, we're going to be moving on to Python. So let me go ahead and close this.
Emiliano, before you do that, a couple of quick points. Yeah, if you just want to open up the Excel. So yeah, that was a great intro. Just a couple of things for people who might not have done a regression before. You won't have the data analysis tool pack automatically. You'll have to, some of you might have to add it on. So whether you're on a Mac or Windows, you can quickly just search up data analysis add-on, and it should guide you. If you're on Windows, I believe you go to File, Options, Add-on. For MacBook, I'm not as sure, but just search up like how to add in data analysis tool pack in Excel, and you should be able to. It's completely free. You just need to click off a certain function. And then for the transpose feature, I know you didn't save Emiliano, but essentially all that was done there is, instead of having it as a column, he made it into a row. So whether you do that using the transpose function, or you just copy them one by one into a row format, it's the exact same thing. And then with the mean squared error, as Emiliano said, you can just search it up on YouTube. Honestly, it's a pretty straightforward metric to evaluate your model. And he's going to go through that a bit more in Python. But yeah, just in case you guys didn't see data analysis, you just have to add it in if you haven't used it before. And,
yeah, no, those are great points, John. Thanks for that. I forgot to mention those. So
no problem. And we have a question in the chat. Asking, so it was a direct message. Maybe someone asked how you transposed. So maybe if you just want to show it on like one column, so it's easier for people to see. Like
yeah, sure. So there's actually a couple ways to transpose in Excel, but if you want to use the function, you do equals transpose, and then you highlight. I'll do it with the columns here so you can see. You highlight the range that you want to transpose. You close it, and then again, I believe on Mac it's Command Enter. On Windows, it might be Control Enter or Control Shift Enter. I can't remember precisely, but you go ahead and you can see here. Now we have officially switched the rows and columns. So it's pretty easy. You can also do it with copy paste, I think, if you, so let me see. So if you copy this and then you go ahead and do paste special, so you go ahead and transpose, it will do it too, right? So there's roughly 2 ways to do it. This is just a formulaic way, and this is just the raw values. So yeah, that's how you transpose in Excel.
Awesome.
Okay, so now that we're going to be moving on to the Python section of the workshop. So for this section, again, we're going to be using the same data set, and we're going to be doing very similar things just on Python. So if any of you guys are familiar with Google Colab, this is just essentially a cloud hosted, it's a cloud hosted Jupyter notebook. You're running everything on the servers. None of this is running your local machine. And this has essentially just an environment for data science and machine learning pre-set up. It's great. If you guys haven't used it, I would highly recommend it. So for the sake of this, workshop, we're going to be ahead and be doing this. I'm just going to be looking to the, if you guys see me panning to the right, it's because I have a second monitor where I have like the complete workshop in, but I'm going to be running through this workshop line by line. And at the end of the day, at the end, I'll be posting just a completed workshop. So the first thing that we have to do is, as you saw, we upload our data. So if you go here, you upload the data, and this will just get pasted into the root directory, which is pretty nice. So this is download CSV, and then we're going to go ahead and simply go over the imports. So here we just have a couple of imports. We're ignoring warnings because some of the stuff, so there's a lot of the Python stuff sometimes throws a random warning, especially if it's a tool that's like a little bit depreciated or something like that. So we'll just go ahead and do that. And the first thing we're going to do is go ahead and read our data. So if any of you guys are unfamiliar with this, we're going to be using Pandas. Pandas is essentially just the most useful library for like data handling in Python. It allows you to read all different types of files, JSON, CSVs, text, TSVs. But in this case, we're just going to be using it to manipulate some basic data. There's a lot of, there's actually a couple of YouTube videos in the Western AI. Yeah, in the Western AI channel for YouTube, in which I believe we have a Python workshop. And if you guys want, you guys should go check that out if you have a little more questions. So yeah, we're going to be reading our data frame, and then I'll just show you like this work quickly. So this is df.head. And as you can see, we've loaded in our data, seems good. So that's fine. So now the next step is to actually go ahead and create a train and test split. I'm just going to be copy pasting this line, but I'll explain in a second. So this is actually from the sklearn library. So as you can see, the next step in for most machine learning projects, or you want to be splitting your data set. For those of you guys that aren't familiar with this process, it's because when we train a model or when we train to predict, we want it to be able to do what's called generalizing to unseen data. So we want our model to be able to predict on data it hasn't seen before. So how we evaluate this model is by actually splitting our data set and evaluating it on unseen data at the end of the day, because we'll be running into something that's called overfitting, and we'll be seeing a little bit of an example of that in a bit. So I'll just explain that. But for now, all you need to know is just like we're splitting all of this data. So all of the rows, 20% is going into our test set, and then 80% is going to our train set. And this random state is just setting, it's just making it so every time we run this function, it's going to split in the exact same way, so the randomness is consistent. So now let's see the info. So as you can see here, it seems like all the data was loaded fine. So an important thing to note here is just like we've loaded all numeric data, and it appears to be numeric. Sometimes when you're working with data, you'll load something in, it'll be a string, or it'll be some random object. You'll get object here. You'll have to like know how to handle those instances by transforming things into numeric instances or string instances. So that's just something to note. And this function just gives you like a quick access to be able to view all that information. And now the next thing I'm going to be doing is I'm going to be doing a quick transformation of one of our variables. So for example, here, one of the things to note is that the year renovated column gives us a lot of information on the price, right? It's just like if a house was renovated, you would expect it to have an increased cost. And if it hasn't been renovated, then you would expect it to have a lower cost, right? It's a pretty intuitive thing here. But like, as you can see here, we're given a simple year of the year was renovated. And this isn't giving us that much information, especially for regression, because if we just run this through, we're gonna get a lot of zeros and a lot of years, right? So a quick thing that we can do to actually transform and get more information of our features or predictors or X values, whatever you want to call them, is actually transforming this into a dummy variable. So as you can see here, I'm outlining two ways to do this, but we're going to be feeding in each of these X values into this function. And if X does not equal 0, then we are going to make it 1. And then if not, we're going to return X, which here we already saw that it's just going to be 0. And then there's two ways to do this in Python. So there's the traditional functional, and then you can also do it with Lambda functions. Lambda functions are useful when you want to just copy paste this in here, for example, and you're able to do it. So now walking through this line of code, here we're running something that's called the apply function. So as I said, apply function, all this does is it applies this instance of this function to every single row of the column of data. So as I said before, we're just going to be running this function through every single row in this data, and it's going to be transforming it and returning a nice column for us. This is called vectorization. For those of you guys that are familiar with R, this is like the most common thing in R, but through some nice implementations in Pandas and NumPy, we're able to replicate the functionality. So here we're going to be running this. And again, you can pass either the Lambda function or the full function. It doesn't matter. The only difference is that if, let's say, I wanted to do it like this, this is doable in Python now. That's a functionality of a Lambda function. So it's just an inline function. For those of you familiar with JavaScript, this is just like an arrow function. So here at the end of the day, we're going to be dropping the year was renovated, of course, because now we have transformed this into like a dummy variable. So maybe I'll go ahead and show you some quick of the transformation quickly. Ahead again. Yeah. So as you see, it's 0, 0, 0. This might not be the best example because we don't see the ones. Okay. You're going to have to trust me on here. We can't see it right away, but there should be some ones here because we did the transformation. So now we're going to go ahead and actually do some plotting. So if you guys are familiar with Python, you might have heard of Seaborn. So Seaborn is actually one of the best, it's one of my favorite plotting libraries, especially because it's very configurable on the palettes. So what I mean by that is, as you can see here, you can set the theme. So we're going to set the white grid, you can set the font, you can set the font scale, and you can set the palette, as I said. And then let's go ahead and do a quick plot. So here we're just saying that this is just a line on matplotlib. So for you guys that are unfamiliar with plotting in Python, there's a main library that's utilized to plot, which is matplotlib. This is just essentially it's built on top of like HTML, CSS, and all that stuff. And a lot of libraries inherit a lot of the functionalities. So Seaborn is actually compatible with, so it has a lot of wrappers and compatibility with matplotlib. So as you can see here, we're going to be using both of them in tangent, and this is great because it means that you only really have to learn one, and then there's a lot of skill transfer between these libraries, right? So we're going to be saying, so this is a line that just sets the figure size to 14 by 11. Then we're going to be doing a distribution plot. We're going to do it on the price, and we're going to be using our training data. It's important to know that you should, when you're doing visualizations and when you're doing analysis, you should try and keep it restrained to your training data, because you don't want to leak any bias or like have an idea of how the data is going to look in the future. This might affect your modeling, and that in turn might make it not generalize better to when you actually feed it in completely new data, right? We're going to specify the bins because it's a distribution plot, which is essentially just a, I mean, I'll just plot, but this is essentially just the little bins, which is a histogram, which is lying a line through it. And then the height, the aspect, all those things, these are all configurable, very nice. And then the tick labels, and then the title. So as you can see, distribution of price. So now the main thing that I wanted to show you here is that if you go ahead and like actually change the palette, yep, Python indentation, the palette, you're gonna see your plot color change, right? So you see how the plot color changes and stuff like that. And then we'll do one more. So you can see it's changing and we're getting nice little color change, and you see the grid on the background is actually going like vertical. So I would highly encourage you guys, especially when you're trying to present communication and visualization, it's a very key skill in presenting any analysis. So I would highly recommend for you guys to look into this function for Seaborn set theme. I see a lot of like, especially notebooks and Kaggle and stuff like that, they're not using this functionality, and I think it's like one of the most useful and nice things to do, just to be able to like custom how your plots look and kind of like be a little more unique with your visualization, the way you do things, right? So now we're gonna go ahead and do a little bit more of a complicated tool. So we're gonna go ahead again. I'm copy pasting, but essentially I'll be running through the lines here. So what we're doing here is we're using matplotlib subplots function. So what this is doing is it's returning a tuple. One of it is our figure, so the whole figure, and the other one is our axis. So you can think of the axis as individual plots. And for those of you guys that are familiar with HTML, CSS, you can think of this as being like the main, the parent div, and then these are the inside divs, if that kind of makes sense. For those of you guys that aren't familiar, you can literally just think of this as like you have your box, and within your box, you have your little boxes. You have your columns and your rows, right? So we're going to go ahead and run this, and we're going to be doing some box plots. So this is our box plots for the bathroom, the price. We're using, again, our training data, and then you can configure the width and stuff like that. These are just configurations to make the X label, Y label, all that stuff. Again, if you're running different stuff, then I would suggest like changing these. We'll be walking through that in a second again, actually. And then we're going to be doing a comp plot. So we're doing Seaborn comp plot, and then we're changing the axis and the like. So here, as you can see, we plotted some nice comp plots. So what we're doing here is we're counting the actual instances of like how many bathrooms on averages things have. And here we're showing the distribution of the bathrooms with the price. So as you can see here, the more, as you would guess, a very intuitive thing to think is that as you increase the amount of bathrooms, the price of the house increases, and you can actually see the distribution between that. So you can see here, for example, houses with 6 bathrooms, you actually have like a mean price of, I think that's $400,000, and which is pretty neat, right? It gives you like a general idea of like that we do have like a monotonically like increasing like relationship between these two, but we do have some variability within our samples, right? So now the next thing I want to show you guys is just like, okay, we did this for bathrooms, but what if we want to do it, for example, I don't know, like whether they're like looking at the data again, whether they're like waterfront or not, right? So something along those lines. So a neat thing to do, and something that like I tend to do a lot, is actually package all of this code into a function. So a lot of times, especially if you go on Kaggle and stuff like that, you see like people copy pasting and stuff like that, and then like rerun the same stuff again, just change the comp. But a little bit of a better practice is to actually go ahead and implement a function. So here we're defining the plotting, so we're passing in the column. Again, this should be, you can actually make this, for example, so this will always be price, but we'll make this, we'll make these F strings, so we'll pass the column name, actually, yeah, this might mess something up right now, so I will go ahead and not do that, but you can pass a second string with the column name, with the name that you want here, and then you can just pass it in. So this is essentially just like I'm sure most of you guys are familiar with functions, so we're just running functions in here, and this will allow us to reproduce all these plots, all these nice plots with other variables. So for example, we're going to pass in waterfront. Actually, I think it will work actually. So for those of you guys that aren't familiar with this is actually called an F string. So this allows you to, F stands for formatted, and this allows you to put in actual Python variables inside your strings, and it will render as if they were just a regular string, right? So this is actually a functionality that you see a lot in other languages. So here you see we've like officially changed the title from bathroom, which we had before, to waterfront, which is with the string we passed in. As you can see, this is not as exciting with a plot because this is just a binary variable, but you can do this with essentially like really any variable you want in here, and this will just make your code a lot faster, more streamlined, a lot easier to read because you're just using the same function, uploading similar graphs, right? So when you're doing analysis at highly suggest, encapsulating a lot of your code and functions. And then I'm just going to be going over like one last plot. Two more plots with you guys. So the next plot that we're going to be looking at is an actual scatter plot, pair plot. So let's say you want to,
just quick question in the chat is, someone's wondering if you can explain the parameters in the box plot function.
Yeah, of course. So I'm guessing you mean this, right? So here, as I mentioned before, let's go look at this one actually. So as I mentioned before, this is, you can think of the figure as your box. This is your box that you're going to put everything in. And then the axes are kind of like the rows, the row / column. So if you want you can have like your row, your first row, your first column, your second column, your second row, first column, second row, second column, and this encapsulates an axis. So this is actually an array of the way that you can actually put things into. So as you can see here, when we're passing into box plots, we're passing the 0th axis, right? Which is considered the 0th row. And as you can see, we're getting this on the 0th row, and we're passing this the first axis, and then we're getting this on the second row, right? So let's say, just to give you an example of something that can actually happen, is let's actually go ahead and switch these. The titles will be off because we're switching them, but like let's go and switch these. And what we're going to see is now we have different things, right? So the main thing to keep in mind here is that this will be one image. So this is one instance of things. So if you go ahead and download these plots, you will get a PNG of both of the images, which is a little bit nice, especially when you want to extract a lot of information or things go in tangent. And they complement each other. It's a nice way to encapsulate it, right? So as far as the other parameters, I think this one's pretty intuitive. It's just the variable that you want to map to the X value, and then this is the variable that you want to map to the price. And then again, we're using our training data, and here we're just specifying the width. So for example, if we want to go ahead and change the width, we can, and we'll get this might throw an error because though. But yeah, we'll just make it a little bit wider, which is it's neat. It allows you to play around with it. As far as the other parameters, these are just little functions to customize. So I think the function names are pretty intuitive. So tick label format, the plain. Actually, this one's a little bit more interesting. I can go over this. So let's go ahead and actually run this commented out, and we'll see that the ticks. Especially for the ticks sometimes get like a little bit messed up. I think this is actually an example where this doesn't happen, but sometimes you'll get like ticks that are very they have like, especially if you have float, you'll get like 2.55555, right? And it's just like this allows you to like kind of like style it a little bit better, and it just does the formatting for you. And then the X label, the Y label, and then the title, these should all be like pretty intuitive. Same thing over here with the count plot. We're just passing a different row, X bathroom, data train, and the like. And then we're just doing we're just making sure that the subplots adjust. So we are specifying the width space and the horizontal space between them, which is in this instance the horizontal. Sorry, the vertical space is the only one that really matters.
Yeah, could you go up just to that first line in the box plot? Yeah, so just because I can see the message a bit clearly. So this, what Emiliano is doing, this isn't the regression. This is just a form of visualization of the initial data.
Yeah.
And so what like the X is literally just like the X axis. So bathroom, as you can see in the visualization, is what we have on the X axis, and Y is the count, and data is where you're pulling those columns from. So the train data set has columns for bathroom and price. If you were to use a different data set with different columns, they would have to come directly from that data set. And so this isn't necessarily the regression. This is just a visualization. So just imagine your typical bar plot, box plot, any plot, and you just want to set your X and your Y axes.
No, that I think you described it perfectly, John. Yeah, sorry if I missed that, but yeah, this is then you have to make sure that these columns are within your data set. And the data here we're specifying is the train, which we declare right over here where we split the data frame, right? So, okay, now we're just going to be running it. Again, this is just preemptive, like John mentioned. This is just a preemptive step when you're doing some data exploration and you're actually just wanting to look into your data, explore a little bit, trying to find the relationships between the variables and what's kind of going on. This is great when you're presenting to somebody because you're able to present where your intuition for the modeling phase came in and kind of like what variables you think are important just visually and why. This is a great representation. So this is a pretty big plot. That's why it's taking a second. So I'll go ahead and actually get us. Oh, there we go. So yeah, so this is what I meant by especially over here when we're using the rows and columns. This function has it built into it, which is a pair plot. So these pair plots is actually mapping the variables against each other. So as you can see here, we have the price, and then this is doing a scatter plot of the square foot of a lot, I think, and then this is square foot of living. So you can see you're able to visually see the relationships, and you can actually kind of like already tell, like if you were to run a relationship between square foot of living, for example, or like price and square foot of living, you can actually kind of like see how you would be able to like draw a line of best fit just from looking at these visualizations, right? Where it goes like this. The nice thing about this too is that we're able to see actually like the distribution of the variable like independently, and you're actually able to see a little bit of like if we have outliers and stuff like that. For example, here in square foot lot, we have some outliers because we have a severely right-skewed distribution. And then here, this distribution seems pretty, it still seems pretty right-skewed because we have some outliers, but it seems a little bit more normal in the place where we don't have actual outliers, right? So yeah, this is one of my favorite plots. Again, it's just neat to be able to like explore the variables and see the relationships between them. And this is very similar to correlation heat map. Some of you guys might be familiar with those, but for that aren't, I'll be going through those. Yeah, sorry. So this one is neat, but it requires a little bit more work. So this is that's, as you can see here, we're running our train data and we're running the correlation function on it. So if we go ahead and let's go ahead and comment all this out. We can go ahead and do train.core. I'll just show you quickly how that looks. So as you can see here, all this is doing is it's giving us a correlation value. So for those of you guys that are familiar with correlation, it's just a simple numerical value of how like between -1 and 1 that allows you to see like as you can see here, 1 is like 1-to-1 relationships, so perfectly linear. So if we increase by like a unit in price and we increase by a unit in price, of course we'll have a unit increase in price. But for example, if we had increased a unit increase in bedrooms and a unit increase in price, then we have a slight correlation of 0.3. So it's just kind of giving you a little bit of just a representation of how the variables map to each other. So this function will give us a correlation map, and what we can actually do with that is we're actually able to have a nice little heat map to see that visually. So here, all I'm really doing is it's just like I'm sorting by the price just to make sure that the price is the first column, or the most intuitive one, because this is our, of course, this is our response variable. And then the next thing I'm doing is I'm just converting this to a NumPy instance to be able to actually plot it, because we need a NumPy instance. And then we're able to do the correlation matrix. So as you can see here, it's a nice little heat map to be able to see how correlated things are. So this gives you a pretty intuitive basis to be able to quickly examine and see what variables might be important. For example, the zip code is highly related to longitude, of course, but in relation to this gives you a nice relationship of like between each other. So for price, for example, we see that the bathrooms are actually that we have a fairly high correlation value, same thing as square foot of living. These are pretty intuitive, so we can expect both of these variables to be fairly significant when we go ahead and actually start our regression analysis, which is the next step. So now this is, of course, this is the regression workshop. So we're going to be doing actually the regression analysis. So the first thing that we need to do for most of these functions, we need to define our X variable and then our Y variable. So this is just some basic functions to actually be able to extract those. So again, this is our training data, and this .iloc stands for integer locate, which allows you to splice and extract data from your data frame using integer notation, right? So it's just like if I was to run this, for example, without this, this should probably throw an error saying that you can't slice based on numeric instances, but when we do integer location, this will run fine. And so what this is saying is we want all the rows, and then we want the column. We want everything after the 0th column. So let's go back. I'll go ahead and actually print our training data so you guys can see like a little bit going here, a little bit more of the intuition. So this line of code is just saying we want all the rows in our training data, but we just don't want the 0th column, right? Which makes sense because we don't want for our X, these are all of our X values, and then our Y value is the price. And as you can see here, what we're saying here is so we want all the columns, but we only want the 0th column, which is our price. So if we go ahead and do Y train.head, we'll see that we just have like a single numeric vector. And then if we do X train head, for example, we have again, sorry, this is capital X. We have all of our vectors for our predictors, right? So this is just some basic data manipulation here in Python. So let's go ahead and I actually have a little bit of some quick definitions to run through, as I mentioned earlier. So I think this is sorry, yeah, okay, there we go. So the next thing we need to do is go ahead and scale our value. So as you guys saw, let's go ahead and do like as we did before. We have a lot of variables, but a lot of them tend to be exploding, and a lot of them tend to be like very, very, very high or very, very, very low. So one of the things that you might want to do when this happens, when you have variables like ranging all over the place, is you might want to standardize them to be able to have them in a little bit more of like a nicer range that makes it a lot more interpretable to the model, and that way you're not getting like huge importance over some minor unit increases in your variables, right? So the way we're going to do this is we're going to be doing min-max scaling, which is just taking your value, taking it by the minimum of that column. So for example, if the minimum of bathrooms is 0, we're going to do 3 minus 0 minus the maximum. As we saw earlier, I think the maximum was like 9. So we'll do 9 minus the minimum, which in this case would be 0 or 1. And then we'll get our min-max value. So it's essentially just taking it and just converting it to the range between 0 and 1, right? So the way that we're going to do that is actually through sklearn. So for those of you guys that are familiar with sklearn, this might just be pretty intuitive, but for you guys that aren't, this is just initializing an instance of the min-max scalar object. And then we're just, now that we have a min-max scalar object, we're able to perform all the methods. So scalar min-max, and then we're going to fit transform. So all this means is we're just running this through every single column and every single row in our data set, and we're just doing this with a single line of code, which is pretty neat. And then, of course, we need to do this for our training data, and we also need to do it for our testing data once we want to test. So let's go ahead and see how this turned out. So as you can see here, this converted it to a NumPy array. So this is not nice and neat like it was for the data frames, but as you can see, it's all decimal now because we're in between the ranges of 0 and 1. This will just allow our model to interpret the code, all the variables a little bit better, and it's just it's fairly common practice. So let's go ahead and actually go ahead through the linear regression portion. So due to time, I don't think I'll be able to run through all the regression examples I wanted to, but this is essentially the equivalent of what we did in Excel. So
before we jump into that regression portion, I think we should take a pause, just see if anyone has any questions. When we'll quickly do that. So please, any questions either in chat or whatever you feel comfortable with.
Yeah, if you guys have any questions, go ahead and put them in chat, and I'll be gladly to go over them.
I got one question that was sent to me.
Sure.
And the question is, how do you access Colab from Google Drive?
How do you access Colab from Google Drive? I think I won't be opening up my drive here just because I have a lot of stuff here. But you can always just go here and then you can just open Notebook, and it should show you like all the notebooks that like you have. So like you guys can see here, I have a bunch of notebooks, and then you should be able to.
You know what? Could you enable screen sharing? I just want to quickly show, just for those who haven't tried Colab before.
Of course.
I'll just quickly share super quick. Thanks. Okay.
So
Daniel, can you
that up,
enable screen share?
Oh yes, my bad. While you pull that up, there was another question. Go ahead, John. Raphael was asking, why do they split the data set 20 training and 80 testing? I think, Raphael, you might have it the other way around. I believe it was split 20 testing and 80 training.
Wait, sorry, could you repeat that?
He was asking why the split was 20% training and 80% testing.
Oh, sorry, it's 80% test, 80% training, 20% testing. Yeah, but the reason that it's split along those lines, it's just common practice. It depends on your data. It depends on a lot of things. There's like actually some mathematical like there's like actually some mathematical theory behind how to split your data best, and it has to do a lot with the distribution of it. I'm not going to pretend like I fully understand it. I took that course a long time ago, but it's very rigorous. And at the end of the day, from what I remember, the professor just said, it's just like, yeah, but like most of the time, like this doesn't really matter. Just make sure that you have sufficient training data to be able to like evaluate your model. So anything between like the ranges of like 70%, 60% training, all the way to like, if you really want, if you're really low in data, if you have a lot of data, then you can even go 90% training, 10% testing. But if you have very low data, then you might even do 50-50, right? So it depends on the properties of your data.
Yeah, as long as you have enough training data is the real concern. So, you know, the split is nice to have, but the important part is that you're training with, you know, enough data, and you're testing with enough data to be confident in your test results.
Yeah, that's exactly it.
I think some people might be confused about the train test, because in Excel, when you do a linear regression, you don't really do a train test. You just rely on the R squared. So to your question, Raphael, the reason why you use a train test split is because the train is what you actually build your linear regression on. So if you're in Excel, that would be your data set that you train it on. And the test set is another data set that you use what you've built on the train set for to see whether or not it applies to that test set. Because otherwise, if you train the model on the same set that you tested on, then maybe it works on that one data set. When you get another data set, it's completely unable to predict anything. And so the reason why we do train test as 80-20 is to build and train the model on that 80% of the train data, and then test it and see if it actually works at predicting values on the 20% of test data.
Right.
So hopefully that clears it up. Now, for those of you who haven't used Colab before, it's pretty simple, and it prevents you from needing to download any other software. So assuming you all have a Gmail account, you'd go to New, just like any other Google Doc, Google Sheet, but instead of these, you'd click More, and then you guys won't have Colab initially. So you want to go to More and then Connect More Apps, and you'll just type in Colab. It's actually Collaboratory, and I have it installed, but if you don't, you just click the installation button. Once you've done that, then you can go to New, More, and then create a Google Colab, and instantly you have an interface from which you can type in Python code and execute it easily. So that's hopefully that clears that up. But yeah.
And again, this all runs on the cloud, so none of this is running on your computer. So it doesn't matter how big your computer is. Like you can use Colab. It's one of the best features. Okay, so I'll just quickly run through the linear regression stuff, and then we might go a little bit over time. If that's okay with you guys, I'll just want to cover like one more thing after this. So essentially, all we're saying is like in a linear regression is we have our variable y, and then we have our coefficients. So we're saying is just like, you can think this literally as just like your slope coefficient. So if you, as Daniel explained in the beginning, is just your rise over run in relation to this variable, but we're doing this in higher dimension, right? So again, this is just a matrix representation of it. So this is just multiplying the beta matrix or the coefficient matrix times the X matrix. Just to note here, because you might get confused, this doesn't include a column where we just have ones and we have the beta coefficient for the intercept. So that's just something to remember. And then again, our primary evaluation metric, most of the time when you're doing regression, especially with machine learning nowadays, if you're not doing machine learning, we get all into like the frequency statistics and all those like information theory evaluations. But for now, we're going to be using the mean squared error, which is essentially saying we have our true value, so we have our true price, and we have our predicted value. We want to see how good this is. So what we're going to do is we're going to subtract them from each other. We're going to square them because we don't really want negative values to impact the sum. So we're going to square them so we always have positive values, and then we're going to sum them all up, and then we're going to divide them by n. So here this isn't divided by n because this is the sum of squares of your error. But if you divide this by m or n, this will give you your MSE, which is your mean squared error that we're explaining earlier. So does anybody have any questions about this, by the way? Because this is fairly important, especially when you're going to be explaining your results. This is one of the primary criteria. I guess another thing to note is that a lot of people might be wondering, it's just like, what does a good mean squared error is? Like, how do I know that like a mean squared error of like 4,000, right? It's just like, is that good or is that bad? And one key thing to know here is just like, it's very dependent on your data. So if your data has, for example, values in the ranges of like 1 million, right? So you have like very, very, like your data is ranging between those values, very high values, but you get a mean squared error that's, for example, another thing to note is just like most of the times when you're interpreting the mean squared error, you're going to be using the root mean squared error. So you're going to be taking the root value. So let's say you have a root mean squared error of like 400. Deviation of 400 when your values are in the range of like 1 million or like 100 million or something like that, very high values. That's very good, right? It means that on average your predictions are not that far off. So that's one thing to know. It's just like the mean squared error is dependent on your data, and you have to keep that in mind. So when you go ahead and Google what's a good mean squared error, you have to remember that it's important with your data. And just because you have a mean squared error of like 0.0001, it doesn't really matter if your data is consistent of very, very, very small values, right? Like, so that's a very important thing to consider, especially when you're explaining your results. So let's go ahead and actually do some linear regression now. So here we're going to be doing linear regression, and then this is from the sklearn library. So if you go ahead to the import section, you can see this. And then we're going to be doing, it has very nice interface, xtrain. So we do that fit with our training data, and then we're going to be running some predictions here. One thing to note is just like if you're familiar with R, you might be more used to like this notation of, this is just for you guys that are familiar with R, where it's just like you just do like x1, or like you'll do like y till the period, and then this will take all the coefficients, right? If you want something more like this, it is available and in Python, and you can do it. It's just through the stats models API. I can, when I send the completed workshop to you guys, or I'll link it, I'll be sure to include a little reference to that. But for you guys that are more comfortable with like R notation and stuff like that, that's something to look into. It's more similar to the GLM package in R. So let's go ahead and run these predictions. And then now we're going to go ahead and see, because now, of course, we want to go ahead and see what's going on. We have all of this, but like, what did we just do? So what we're doing here is we're taking the absolute value of the coefficients, and then we're attaching the names. The names are just the columns that we had. And then we're just reversing this because to have our most important coefficients at the top and our least important coefficients at the bottom. So here we see that grade, bedroom, square foot above, and square foot living are considered some of the most important variables. How we know this is because they have the highest coefficient value. So a coefficient value in linear regression, again, is just a rise over run. So if you can think this as a unit increase in X, right, means it's scaled by this factor, right? It will yield a unit increase in Y, right? So so what happens if we increase by 1 unit? So if this goes from 1 to 2, we'll be just doubling the value of this coefficient. and in return, we'll be getting that additional value in y, right? So it's just like it's a simple rice over run. This coefficient is these coefficient values should be fairly intuitive. So bigger means more impact, smaller means less impact, but you have to think of them in absolute terms, right? Because if this was, for example, negative, that would just mean that the slope is going down, right? So we're actually decreasing in slope. So this is a fairly neat tool. And then again, I have a couple of other models that I want to go over, especially regularized models, so ridge and lasso regression. But for the sake of time, we're going to actually be going over to some more model evaluation stuff. So let's go ahead and import the cross-validation. So when you're actually interpreting your model, a really important thing to do is to evaluate it based on unseen data. But I see a lot of people do this, especially on Kaggle beginner, intermediate. What you'll do is just like you'll run all these models, and your main way of evaluating it is just by plugging it into your test set, right? So you got your model, you want to see how it performs on the test set to see if it generalizes well. And well, now you're essentially just basing your best model on the one that performs best in the test set. But most of the times, this is not what you want to be doing, because you're adding general bias that this test set or this subset of the data that you picked to test on is going to be representative of fully unseen data, right? So a lot of times your test set might not be fully representative of what you'll see like in the future. So a good way to actually, a better way in my experience to actually test this is by using cross-validation. So cross-validation is literally just, let's say we have our data set and we want to run a simulation of training a model on this data set in K folds. So here the folds are 10. So we're gonna have 10 data sets, and we're gonna have this data set, and we're gonna have a small section of it in each iteration be a testing data set or validation data set. And we're gonna change the validation data set each iteration. So our first iteration might be this section of the data set is our validation data set, and then the next one, this section of the data set is our validation data set, and we're going so forth until, in this case, we have 10 partitions of the data set, right? I hope this makes sense. It's very intuitive. I would suggest you guys look it up. Once you visualize it and you see a little picture of it, it's very easy to see. But it's in my opinion, as you can see, this is taking a while because, of course, it's running and iterating many models. But this allows you to see how your model generalizes, right? So it's just like what this is really doing is it's just like this is testing the models. This is building a new model each time on a new training data set or a new subset of data sets, and you can actually evaluate. You get a better estimate of what your true MSE or your true criterion is going to be rather than if you don't do this. So here, as you can see, I was doing this for one of the models that we're going to go through was a random forest regressor. So here we're going through like a random forest regressor, and then we're training 10 random forest regressors here. Again, we're using the negative mean square there. Don't freak out. This is just sklearn's way because for an optimization, we just need the negative mean square there. It's just the way that sklearn is built. This negative doesn't mean anything. Don't freak out about that. But it will return negative values. So as you can see here, I'm multiplying it by -1, and this will give us our mean. This will give us our mean estimate of our mean squared errors for 10 models. So you can think of this as just like training like 10 models. So 1, 2, 3, or I'll just go through 5, and then each one of our here I'll just show you the scores. Actually, I think that's it. It's better, right? So it's just like we have 10 models, and we're checking how all these 10 models perform, and then we're averaging them, and that's our estimate of how well our model is going to generalize to train to the true data. So one of the things that we can do now is we can actually go ahead and compare this to like how it really did against the random forest. So this is just from the random forest model that I was going to build. So let me just very quickly do that. So Another thing that I was going to show you guys was how to actually do a function that is able to just do models for you a little bit easier, and it shows you all the statistics for it. But again, this will be in the full workshop that will be sending to you guys in a second. So here we're just creating a random forest regressor and then we're going to be grabbing the best model, the best estimator from the grid. Oh, sorry, this was from the grid search. Yeah. So yeah, sorry, due to time, I had to get a little bit scrambled. But essentially what this is doing is it's just like, let's say you want a random forest regressor with different hyperparameters and you want to test which ones are best. So a good way to do it is with actually grid searching. So we'll be doing like cross-validation a bunch of times. And we'll be essentially doing the cross-validation and see how they perform with each specific hyperparameter, right? So here you can see that for random forest regressor, we'll have the amount of estimators. So we'll have 100 estimators, 50 estimators, 100, and then 200. And we'll see how they perform on the cross-validation split. And at the end of the day, we'll be picking the model with the best that perform the best in the cross-validation with the given hyperparameters. So here, while this trains, I'll have like a little bit second, like if you guys have any questions, while this trains, it's a great time to go ahead and ask. Are there any questions?
I'll just say a couple of things, Emiliano. So clearly, Emiliano and Daniel are very well versed in machine learning. They have done it for like extensive amounts of time. I know that this can be intimidating for those of you who maybe haven't done machine learning or even Python before. What I would say is, and this is like some sort of advice for those of you who are on the call right now, if you're more familiar with Excel, I would start there, run your regression in Excel, do the data cleaning there, because it's easier, to be honest. But once you've done that, once you've cleaned your data set, meaning like once you've gotten rid of all the rows with no data in them or with sort of messy data or with text rather than numbers, then try and bring it into Python and just try and experiment. We have a lot of tutorials on our YouTube that will walk you through it very systematically. It's not a complicated process to get something going. What Emiliano is doing here is like is building up on that, but the basic fundamentals of building a linear regression in Python are very simple and straightforward. And so I would encourage you to try that out and just give it a shot. And there's a ton of resources online that can help you do that if you choose.
Yeah, so here, hopefully this finishes training, but this will essentially just be at the end of the workshop. So let me go ahead and unfortunately, I didn't have time to go through the full plan workshop, but that's okay because I'll be sharing that with you guys. So let me go ahead. So that's another great thing about Google Colab is that you guys are going to be able to just access the workshop and be able to see. So I've linked the workshop in the chat. Go ahead and check that out. This is the full workshop with all the comments and stuff like that and all the code. You guys should be able to run it from start to end, and you guys should be able to use a lot of it. A lot of the similar functionality or similar ideas in like your own projects, or be able to just replicate and see, like try to like understand the code a little bit better. So yeah, unfortunately, this ran a lot faster on like, again, this is running on the cloud, so this ran a lot faster on my computer. But the whole point of this is to be able to get the best model based on the hyperparameters that we're going through, right? So yeah, I guess for now, I'll just wrap it up based on that we're a lot of time over, and I want to get you guys a little break before you guys start the competition, so sorry about that. But yeah, if anybody has any questions or anything like that, please drop them in the chat. If not, yeah, then you guys feel free to go, or if you guys want to wait for this to finish running, then that's okay too.
Yeah, and last thing, so what we've been doing here today is like showing you guys how to build a regression model, and Daniel and Emiliano have taken you through the process of doing that. When it actually comes to how we're going to grade the competition and decide who the actual winners are, you guys will see this when the case and accompanying documents are released at 3 o'clock. But essentially, it's going to be split between your presentation and the technical piece. So even if you have the very best model, if you are unable to explain that to a non-technical audience, you will not win. I can tell you right now that the majority of the points allocated are not for the performance of the model. That is a component of it. But if you can't explain it, which is to say, if you just try and copy a model that you see online, you will not do as well as you may think. So take that into account, do the best you can, and know that as long as you're able to explain what you've done clearly to the judges, that will inform how you perform the competition much better than spending hours more adding more parameters to the model itself. Although that is something to look into, I would just say think about both of those things when you're going through the competition. But yeah, great job, Emiliano and Daniel. We will post this to our YouTube channel as soon as we can, because Daniel's recorded the YouTube video. And also, if you guys would be able to check out our Discord, maybe Rohan, if you want to send the link in. The Discord is where you'll be able to ask questions throughout the competition. If you're confused about the wording of the case or about anything to do with the submission or the rubric, feel free to put the questions in our dedicated Discord channel for DataQuest. You'll have to add the DataQuest tag, I believe. We don't want to be spamming our emails because we need to coordinate some other stuff with our judges. So please join the Discord and add the tag for DataQuest. You'll be able to ask any questions and we'll get back to you as soon as we can.
Yep. We did have one question. Sorry, John. They're asking why I picked the random forest regressor as the model. So unfortunately, if you go look at the full workshop that I sent a link to, I go a little bit over the random forest regressor, which is actually like it's a very powerful model. Okay, here we finished. It's a very powerful model, and if you know about the bias variance trade-off, which I won't get into here, but it's essentially very flexible, but it's also fairly, to an extent, it's fairly interpretable. So it's a really good model to be looking into, and it's actually something called an ensemble method, and that's a big word, but all that really means is that we're picking a bunch of decision trees. So you can literally think of this as like, if you're familiar with like general computer science, you can think of this as like a binary tree, but just with decisions. So if it's less than this, go here. If it's more than that, go that. And we're picking a bunch of those trees to build our regression model. And we're actually running, when we run our prediction, we ask all of those trees, what do we think the prediction is? What do we think this is? And at the end of the day, we just take the most bullet on prediction, or you can do the average prediction. There's a whole thing of ensembles, but most of the time we just pick the most common one, and then we go ahead and we just say that's our value. So it's kind of like a democratic system of trees, if you will. Then here we saw that we finished. So as you can see here, with cross validation, we got the cross validation of 12,700, 127,480, and then over here we got 146,455 when we actually tested on the data set. Again, this is still fairly close, and as you can see, this was like a fair estimate of our test error. And in general, this will generalize better to training data because to unseen data, because again, if you just keep trying to like new models and just trying to get the best test MSE, all you're gonna do is you're just gonna like overfit to your test set by trying to find the best MSE for your test set, right? And then you plug it into like completely new data, and then you're gonna get the same errors where things are just kind of like not looking the same. So a better way to do it is using cross-validation to estimate that. So yeah.
Yep, and you absolutely don't need to use random forest regression if you don't want to. Think about it like the competition starts now and it's due tomorrow, and your goal is to build the best model you can. Random forest is one of the ways you can do that. There's also many other types of regression. So I would just search up regression. You'll find a long list of different models, and whichever one of those you feel is most appropriate, which is, as we talked about, one of the downsides of Excel is you don't have access to that many models. You don't have access to as many models, whereas Python, as you see, there's a lot more options. But in reality, build the model that you think is able to predict the data with the highest level of accuracy, and that's all you need to do. However you do that is up to you.
Yeah, no, I think you put it great, John. There's a bunch of regression models. If you really want neural networks, you don't need to, if you guys want to look at the full workshop, there are some steps over lasso and rich regression, which is in general, that's regularization, which suggests you guys Google that. It's fairly intuitive. All that it means is just like important variables stay big, the coefficients stay big. Not important variables, they get small because we don't want them to impact our end result, right? So yeah, this essentially wraps it up. Are there any final questions before we go? No.
If no one
Okay.
has any questions, you just want to say thanks, guys, for coming out. We took a little bit extra of your time, so for those of you who stuck around, thanks a lot. The case drops at 3 p.m., so be ready for that. And yeah, good luck to everyone.
Yeah, best of luck. Thanks for coming out, guys.
Good luck, everyone. And thanks to Emiliano and Daniel for hosting the great workshop.